podcast is brought to you by LMU Munich.
Like all of the speakers, I want to thank the organizers for the kind invitation and for a wonderful conference that is taking place here. So the topic that I chose to talk about is to discuss some aspects of non-perturbative physics in F-theory compactification. Primarily, there is actually particle physics motivation for the studies, and so some of the things I'm going to focus on are not unrelated to those that Angel Uranga was discussing. So, if we are talking about instantons in F-theory, we basically think about Euclidean D3 branes that make some effect on effective theory of such F-theory compactification. Well, F-theory as such is a theory defined at finite string coupling, but without any detailed fundamental formulation. So one tries to approach this difficult problem with different ways, so the multi-prong approach. And some of the efforts that I have been pursuing with different collaborators in recent past focus on trying to understand the nature of zero modes in F-theory in the presence of Euclidean D3 branes, in particular focusing both on neutral zero modes that basically tell you whether this configuration could contribute to non-perturbative superpotential, or also the so-called charged zero modes, which are associated with intersections of the Euclidean branes with the presence of gauge branes that carry gauge charges. And so this approach is in some series of papers, in particular with Iñaki Garcia Chavarria and Robert Richter. We use monodromies to get an idea about the neutral zero modes, but in subsequent works, also with Jim Halverson, we employed also other techniques like anomaly inflow and also stream junction techniques. But that's not what I want to talk about. I really want to talk about more recent focus when we really try to get direct information about properties of a superpotential. In this program, one is trying to approach that again with different techniques. So the main topic of my talk will be to try to focus on the properties of the superpotential contribution from such instantons, and more specifically to get the information about the features of prefactors in the exponentially suppressed terms in the superpotential, the so-called Pfaffians that carry basically the gauge D-brane moduli dependence. So to tackle this issue, we approach that first by using heterotic duality, where we actually, through duality map, realized that the structure Pfaffia of those Pfaffians has very geometric features, and one could interpret zero loci of such Pfaffians as appearance of enhanced symmetry points of gauge curves on the word volume of instantons. Another approach that I will try to highlight here is the one when we try to propose actually to obtain information about such Pfaffians directly in F-theory without heterotic duals, and thus also naturally include all the potentially all the subtleties associated with the fluxes in F-theory. Another approach for which unfortunately I won't have much time is also trying to tackle the issue of instanton contribution via M-theory duality, basically using supergravity techniques in a dual, actually lower dimension n equal to M-theory approach. But that's not what I want to talk about, and it's still a work in progress. So my focus will really be on highlighting aspects of our work where we try to get direct F-theory proposal to calculate and get information on such Pfaffians. So this is the work together with Ron Donaghy, Jim Halverson, and Joe Marsano, and it's in a work that is actually hopefully about to appear. Well, probably I should make a little introduction and try to motivate why we try to study the instantons. And of course, one and very important aspect is to address moduli stabilization in string compactification, and in particular that led to tremendous activities when a combination of fluxes and the instanton contribution to superpotentials could actually lead to the information about the moduli stabilization for different type 2 compactifications, leading to the so-called KKLT scenario, also the Swiss G scenario, and so on. Well, another type of instantons that is close to my heart are the instantons that actually, under certain conditions, can generate perturbatively absent couplings for charged physical matter. And in this case, actually, the instantons can affect couplings, for example, in the charged sector that describes the standard model of string compactification. And actually, as Angel has mentioned at the beginning, this idea was actually spelled out in 3 independent papers with slightly different motivations. But the core thing is that actually one focuses on non-perturbative violation of so-called anomalous U1s in the presence of more general instantons, which then, due to the breaking of this anomalous U1 to discrete symmetry, produces couplings that were originally forbidden for charged sector due to this U1 conservation. Well, I can help myself to show you actually the core idea for this charged sector corrections, and the easiest way is to go to the most geometric intersecting brane, type 2A proposal, and sort of describe the background of Euclidean D2 instanton as a point in ordinary flat space, but wrapping a 3-cycle in internal space. So the presence of such Euclidean configuration can in principle modify couplings in effective theory. The typical contribution would be exponentially suppressed by the classical action of such instantons, and it would be proportional to the volume of the cycles wrapping that the Euclidean brane wraps. Now, the appearance of charged sector corrections are there when we have a regular brane that wraps another cycle, but this other cycle of physical brane with gauge degrees of freedom can intersect at fixed points, number of points, with the original instanton, thus introducing the charged zero modes at the intersection of instanton and the gauge brane. And it's these charged zero modes that contribute to a violation of anomalous U1 and are responsible for non-perturbative generation of charged coupling matter. Well, this other type of instantons were actually introduced primarily because we had phenomenological motivation. We wanted to actually introduce certain perturbatively absent couplings for charged matter in the standard model or grand unified theories. For example, such effects could modify and give us Majorana neutrino masses or directly Dirac neutrino masses. They could modify the absent 10-10-5 coupling in type 2 SU5 gas. They could introduce potentially supersymmetry breaking terms and so on. And actually the concrete calculation or demonstration of this effect was originally presented in local embeddings, but further work also promoted the study of such charge sector instanton, also with global embeddings, all the way to F-theory, and also actually with the byproduct that the new algorithm for calculations of zero modes on toric variety was developed, very useful in general for string compactification. Well, anyway, this was sort of more going to the sideline. Let me now turn directly to F-theory compactification, as Angel mentioned. We have seen a major revival in the study of F-theory compactification, primarily motivated by the fact that it actually sort of combines and unifies the geometric feature of particle physics that we can derive from intersecting brane picture, along with exceptional gauge symmetries, and thus allowing us to have more realistic Yukawa coupling structures in this context. So the basic geometry is based on elliptically fibered Calabi-Yau fourfold, where complexified string coupling is encoded in T2 fibration over three-dimensional base. The gauge symmetries appear where the fiber degenerates to codimension 1 singularities, and the type of singularities that appear are associated with the gauge symmetry that lives on the corresponding 7 branes in the three-dimensional base. The matter appears geometrically at the intersection of such 7 branes, and so corresponds to codimension 2 singularities. But for chirality, we also now have to introduce the fluxes to get actually chiral matter. Well, this is something that Angel touched upon, so let me just mention that there was tremendous amount of work done, and I cannot do justice to people, some of them also in the audience, in constructions in particular, both local, semi-local, and global SU5 GATT models, starting with original work, recent revival by Donaghy and Weinhold, and Beasley, Heckman, and Waffa, pursued by a number of people. And in recent efforts, in the past 2 years, actually, the effort is becoming quite technical and focusing on trying to understand in more technical details the effects of turning on flux in such compactification. So this little cartoon that I like to show of how we sort of visualize the appearance of gauge symmetries when T2 fibers degenerate, the matter at intersection of the corresponding branes. And if we want to now put in this context also the Euclidean D3 instantons, we are talking now also about the divisors in the base that the Euclidean D3 brane can wrap, and actually what one is after to get first-hand information about the nature of the zero modes in the presence of such Euclidean configurations, and of course, the second step, their superpotential contribution. The instantons in F-theory were not discovered in recent years. There is extensive work that stems all the way to from the early days of F-theory, by Witten, Katz, Waffa, Ganor, and others. But in the context of string compactification and more connection to trying to understand their effects for effective four-dimensional compactifications, the work of Blumenhagen, Colinucci, and Jurke introduced a lot of important concepts, and the program also by Grimm and his collaborators, and by Weigand and his collaborators, as well as other groups that have been currently pursuing the effects in F-theory instantons. And this more recent work really is trying to understand better the flux effects and also effects of the abelian U1 factors. Well, what I want to tell you in the rest of my talk, how much do I have? Probably enough. So what I want to tell you in the rest of my talk really is now focus on some progress we try to make directly in F-theory to understand superpotential contribution that primarily works toward the questions of moduli stabilization. So trying to understand the effect of the structure where this prefactor is a Pfaffian which carries dependence of the 7 brane moduli restricted to the instanton configuration. So we want to directly study moduli dependence of this prefactor A that I'm going to refer to as a Pfaffian. So the approach that we are taking is to some extent focusing really on a specific Euclidean D3 instanton that traps a divisor in 3-dimensional base and assume only a presence of a gut 7 brane divisors that traps another base divisor B2. So the key structure of such effects of the superpotential will be captured by intersection of the Euclidean D3 brane with the gut brane divisor, which and they intersect actually at a curve sigma, and in addition, of course, we expect that the key physics to superpotential will be captured by physics at this intersection, and whatever G4 fluxes will be restricted to this local information associated with the intersection of instanton and gut brane divisors. So let me maybe highlight the results and then go to some more detailed technical discussions as well as description of models or concrete examples. So the key upshot of this approach is that we arrived at a conjecture how to compute actually Pfaffian A in the presence of such a gut brane and the Euclidean D3 brane. One can, with this proposal, do concrete F-theory calculations, leading us to specific concrete dependence of these prefactors on actually this 7 brane moduli restricted to this intersection on the curve sigma. We can analyze for the substructure of such Pfaffians, including actually points of higher enhancement, like E8 enhancement curves on the word volume of the instanton. So those are the key things that we address and propose. And now let me get to more concrete realization of some of those things. I do want to say, while our proposal is directly in F-theory, we often do try to use actually the dualities to relate things by which we describe the F-theory and instanton wrapping a particular divisor in F-theory to dual description, in particular one that is very straightforward and interchangeably used is the duality to M theory. In this case, actually, the duality of the elliptically fiber fourfold actually can be mapped onto description now of this Euclidean D3 instantons to be now described in M theory as Euclidean M5 brane, but the geometry of the M theory corresponds to shrinking the elliptic, the torus to 0 size while still keeping the complex structure fixed, and so the corresponding Euclidean M5 instantons actually has a lag in the fiber and refers to also as wrapping vertical divisor. I don't have time, but I can't help by highlight a short slide that actually addresses some of those things directly in M theory, some of the issues of F theory physics, by using actually 3D M theory duality, namely describing four-dimensional F theory in a Coulomb gauge in terms of further circle compactified theory down to 3 dimensions, which we now relate to M theory compactified on a dual, a non-singular fourfold in this case. And since on the M theory side we have basically supergravity techniques, we can match the calculation of the action on M theory side directly actually to effective F theory action, but the match actually is subtler because classical results are related to actually effects in the F theory at the whole one loop level. And there is one very rich structure related to getting information from direct M theory calculations, which has to do with the 3D Chern-Simons terms, whose coefficient actually encode tremendous information about properties of the dual F theory. In particular, the chiral index is specified by these 3D supergravity Chern-Simons terms, which can be calculated via G4 flux calculation, but they are related directly through one loop coefficients of F theory Chern-Simons terms when we actually integrate massive modes in the Coulomb phase. And so it's this index that actually specifies the chirality of four-dimensional theory. Also, the issues of anomaly cancellations are deeply related to the structure of such Chern-Simons terms. That's the work that is about to appear. And also, actually, there is the issue of the index of the instanton zero modes. This is also related to such Chern-Simons terms. Of course, this is just a digression, but I would like to say that Dennis Clevers will actually have another 5 minutes to discuss that at the Gong Show talk. All right, so let me go to the key points, our conjecture and examples in the rest of my talk. Maybe I should just skip further details of the examples of F theory heterotic duality, but when we do have heterotic and F theory duality, actually the fourfold has a base that is also elliptically fibered, and its corresponding two-dimensional base is the same base as an elliptically fibered dual heterotic threefold. And in this case, actually, we can describe through this duality now some of the data associated both with the geometry and the fluxes on F theory, as well as instanton that wraps now actually the curve in the base and the elliptic fiber of the three-dimensional base. We can now map that actually to full data on a dual heterotic threefold. In particular, the flux data can be mapped on the corresponding vector bundle data, and the actual Euclidean D3 instantons can be mapped onto the worldsheet instanton properties in the dual heterotic threefold. And since we understand the actual zero mode structure, in particular the so-called left-moving zero modes on the heterotic side via spectral data cover, and namely realize it if a line bundle on a certain spectral curve gets a section, we can identify that with the numbers of corresponding fermionic zero modes, left-moving zero modes, and that can now map, in this case, onto the F theory interpretation. But that's not the conjecture I want to talk about. I really want to talk about the data, instanton data directly in F theory without heterotic duals. So we have a general three-dimensional base. We have Euclidean divisor of the instanton intersecting with the God divisor at a curve. The actual gauge theory data can be specified on the God divisor in terms of the Higgs bundle, and this information can be encoded in the so-called spectral cover data of spectral surfaces and line bundles that carry information about the flux on the God bundle. And so when we want to get now down to the information how these degrees of freedom affect the properties of the instanton, we basically have to focus on this intersection curve and identify line bundle cohomology on a local spectral curve that is related actually to the spectral surface of the whole gauge God brane, but restricted now in a specific way to the intersection curve. And analogously, the line bundle data on the full gauge God divisor can now, in this specific case, be restricted down to specifying a line bundle cohomology on this local curve. Okay? And having this precisely formulated in terms of the spectral data allows us now to calculate the corresponding Pfaffian directly from this data in F theory. Due to lack of time, those are just the specific ways how we formulate classes of this spectral curve and the corresponding definition or a calculation of the line bundle associated with the local curve now allows us propose a conjecture that whenever the line bundle associated with this local spectral curve gets a section, namely new zero modes appear, in this case the Pfaffian prefactor turns to be 0. Now, we can do even more. We can actually calculate the whole Pfaffian as a function of moduli dependence of a cohomology of these line bundles on the spectral curve. And calculation is very analogous to heterotic computation. It involves the exact Koszul sequence, which then translates to cohomology calculations in the long exact sequences and allows us to get the Pfaffian. Now, this proposal actually, the way it's formulated directly in F theory, passes key checks. One is when heterotic dual exists. Actually, this calculation is isomorphic via cylinder map to dual heterotic calculation of line bundles on spectral heterotic curves. When we have type 2b limit, the interpretation of the cohomology I was referring to naturally has interpretation in terms of charge, the so-called lambda modes. And connection to M theory is still less well defined. This is more technical, showing that actually in the case when heterotic dual exists via cylinder map, both cohomology data on the spectral curve in F theory and spectral curve in heterotic theory is isomorphic. We can now proceed and set up the actual concrete calculations, determine specifically the spectral curve for specific examples and the specific line bundles, calculate Pfaffian then by a Koszul exact sequence and get the results. So let me show you some of the results. But what we expect is actually with this calculation to get Pfaffian prefactor that have intriguing structure, namely in terms of polynomials in complex structure of 7 branes that are restricted to the instanton word volume. There is a local substructure there, and actually the Pfaffians depends only on a subset of the 7 brane moduli as geometrically expected, those that actually are associated directly with the intersection of the instanton. So let me show you an example of this calculation directly in F theory. So it's an example of a toric 3-dimensional 4-fold base which I'm specifying in terms of the toric data, holomorphic coordinates, divisor classes, and corresponding scaling weights or charges. It's an example where actually the gut divisor is at Z0 holomorphic coordinate, and the corresponding instanton divisor is at x1 equals 0. We can actually trace the appearance of the gut divisors from the Calabi-Yau defining equation, seeing what happens as we go to Z equals 0. And actually, it's those sections of complex structure 7 brane moduli that depend on complex structure 7 brane moduli, the sections B0, B2, and B3 that can be directly determined now in terms of the toric data and corresponding canonical bundles. So we calculate our toric data, our spectral cover data, obtain the defining equation for the spectral curve, which depends now only on the subset of moduli that are restricted to the intersection of the instanton and the brane. And the result via Cauchy exact sequences is the Pfaffian, which, while complex, has intriguing structure. It appears with the 4th power of the polynomial of this specific 7 brane moduli. And it actually turns out that such a structure, while for this concrete F-theory example is of that form, it's actually the structure like that is quite ubiquitous, and actually the polynomial, when this polynomial becomes 0, I can show that this is exactly the point where there is E8 enhancement point in the instanton word volume. And this enhancement E8 points are very, happen quite often. And so we see it's an example actually when we get enhancement, E8 enhancement point in the word volume of the instanton, our Pfaffian becomes 0. Why I'm mentioning those things is that one would like to see if there is more physics to that, if one can get this observation in more quantified way, and actually we can quantify precisely under which condition we can actually get Pfaffian zeros where we have E8 enhancement points, and that can actually apply it also to SU5 guts. And that is intriguing because there are potential interesting implications of this observation, because points of E8 enhancement seem to be special and could give us a natural flavor structure potentially in SU5 F-theory guts, also some aspects of supersymmetry, breaking scenarios, and so on. Okay. Since this calculation I propose is actually quite well defined, and we can decide and start scanning actually large classes of three-dimensional bases. In particular, we took a list of Kreutzer-Skarke polytopes and constructed toric B3, a three-dimensional toric basis. This is the actual spectral cover data associated with different examples of this toric spaces, and one can, with this data, spectral cover data, actually can calculate Pfaffians. For example, we see that often we get Pfaffians that are 0 directly for this whole class of the three-dimensional basis. We have examples where we have E8 enhancement. That's the example that I just showed you. And there are other examples that are more complicated, and Pfaffians have not been computed. But one story is quite intriguing. We see that we often get identical zeros. This would basically imply that superpotential does not contribute and has potential implications whether we can stabilize moduli. But potentials come from here by modifying charge couplings. Points of E8 are often, we see actually very high degeneracy of Pfaffians. Many compactification can give us the same effects. This is an example, now technical example, where we don't have Pfaffian yet, but the transition matrix whose determinant is Pfaffian is such a big matrix, so we expect this to increase, and analytic computation by the computer programs may not be feasible unless we figure out a better way of doing that. Anyway, let me conclude. So I try to focus on some of the effects that we get due to instantons in F-theory, and I try to present most recent results where we are approaching the study of Pfaffian prefactors in superpotentials. We propose a conjecture to calculate those Pfaffians directly in F-theory via line bundle cohomology on spectral curves over the specific instanton and the gut-brain intersection. The checks by heterotic duals and type 2 work, M-theory connections still less tangible. Already some of these results point to intriguing restructure of such Pfaffian. We see that we have typical factorization into non-trivial powers of moduli, 7 brain moduli. Points of E8 enhancement often happen and cause at those points Pfaffian to vanish. And there are intriguing potential consequences both for modular stabilization and particle physics by understanding these features better. Thank you.
Thank you very much. So we have time just for one urgent question. Yes?
Since F-theory is non-perturbative, would you expect multi-instanton contributions to be as important as single-instanton contributions?
Not necessarily, because it actually, this particular example does depend on the choice of the size of divisors. There are additional scales in F-theory compactification that can actually provide hierarchies here as well. So it's not, you're not completely forced to that, to sum up everything, depending in which, domain of modular space you are of this fourfold.
Okay, let's